Since the dawn of time, humanity was destined to grow. Cities, tools, law, transportation, and so much more was the fruit of a few thousand years of non-stop evolution for our species. However, the basis of modern-day civilization was set by a massive breakpoint, the discovery of agriculture. It allowed us to shift from a hunting-oriented species that had to leave whenever there was food scarcity to a more advanced society that was able to grow its own food. Soon after, we found out that it did not come with no challenges. Historically speaking, farmers always faced many setbacks when it came to plant diseases. And even after learning how to adapt to that, there was always the problem with how long it took for someone to learn the job, as it is not easy to pinpoint the exact moment the plant is ripe. Here at PlanTech, we have trained AI models to help farmers with three main points. 1. Early plant disease detection using classification. 2. Detection of good and bad garlic seeds using object detection. 3. Detection of maturity stage of crops using object detection. We are currently working on optimizing our models, which we then plan to deploy on an easy-to-use app anytime and anywhere. In the next part of the video, we're going to show an in-depth look at our project and how PlanTech is the future of agriculture.
The first part conducted in this project is image classification to identify plant diseases on leaves. Before that, let's talk about the data set. We have here 3 different crops and the diseases that may affect them. During our work, we have used 2 different data sets that are based on the Plant Village dataset available on Kaggle, contains 38 distinct classes, 12 of them are healthy and 26 are diseased. During the training of our models, we have used the new plant disease dataset, which contains around 87,000 RGB images, while for evaluating our models, we have used the plant diseases dataset, contains about 217,000 RGB images. Next, let's see the transfer learning architecture used. We have first the input data, which is of size 224 with 3 channels fed into the build architecture, and then we have a batch normalization. After that, we have a dense layer with 124 units, and then we use dropout of 0.5 to reduce overfitting. After that, we flatten the data and fed it into the output layer, which is dense layer with 38 units because we have 38 classes with softmax as an activation function. Now, the results obtained during the work are shown here in the table. As you can observe, we have used 6 different architectures, which are the VGG16, Inception v3, MobileNet v1, MobileNet v2, DenseNet 121, and NesNet Mobile. We have the training images and the testing images along with the evaluation on different matrices. Now, as a discussion, we have seen that the performance of all the architectures was promising in general. The lightweight deep learning architectures, which are MobileNets, DenseNet 121 and NesNet Mobile, was better than the old classification architectures. The NesNet 121 architecture had the best performance in terms of the matrices. However, the model deployed on the smartphone application was the MobileNet v1 because it showed the best performance in terms of evaluation matrices and the size, as well as being the only architecture supported by Flutter.
In this part, we tackled with the detection of different crops ripening or maturity stages, and the detection of seeds viability, whether they are good or bad. We choose garlic for this. The architectures used in this part, which were YOLO v5 and SSD MobileNet version 1. The choice was because of their best performance among available object detection architectures. And lastly, the results. As the models we used were able to detect most of the samples in the input data, which were live images from the phone camera. Datasets used: Laboratomato. Laboratomato is a public dataset in GitHub, which is an image dataset of growing tomatoes at different stages of their ripening, which is designed for object detection and instant segmentation tasks. Each tomato is divided into 3 categories depending on their stage of ripening. Fully ripened, completely red color and ready to be harvested, filled with red color of 90% or more. 1,671 samples. half ripened, greenish and needs time to ripen, filled with red color to 30 or to 89%, 1,656 samples. Green, completely green white, sometimes with rare red parts, filled with red color on 0 to 30, 6,450 samples. Our percentages are approximate and differ from case to case. Fruit detection dataset. It is an image dataset of growing fruits at 2 stages of their ripening, which is designed for object detection and instant segmentation tasks. The dataset is taken from a RoboFlow platform. The training set got 850 images and the testing set got 190 images. The images were collected from an internet. And the same goes to the garlic image dataset, which was taken from RoboFlow platform. Architecture used: YOLO v5 and SSD MobileNet version 1. YOLO v5. It's an object detection which is designed to create features from input images and then to feed these features through a prediction system to the robots around objects and predict their classes. The YOLO model was the first object detector to connect the procedure of predicting bounding boxes with class labels in an end-to-end differentiable network. The YOLO network consists of 3 main pieces. Backbone, a convolutional neural network that aggregates and forms image features at different granularities. Neck, a series of layers to mix and combine image features to pass them forward and prediction. Head, consumes features from the neck and takes board and classes prediction steps. And next, there is MobileNet, which is an architecture model of the convolutional neural network that explicitly focuses on image classification for mobile application. Rather than using the standard convolutional layer, it uses depth-wise separate convolution layer. What makes this model stand out is its architecture lessens the computational cost and very low computational power is needed to run and apply transfer learning. Single-shot multi-box detector, or SSD, is an algorithm which takes only one shot to detect many objects in the image using multi-box. It uses a single deep neural network to achieve this. This detector works on a variety of different scales, so it is able to detect objects of various different size scales in the image. Given below is the architecture of the YOLO v5 and SSD MobileNet, which is the combination of SSD and MobileNet that we mentioned earlier. Summary of the result. In this part, we used different metrics to evaluate our 2 models, which are YOLO v5 and SSD MobileNet version 1. These metrics are the average precision in different scales, and we can notice that YOLO v5 is outstanding the SSD MobileNet version 1 heavily, but SSD MobileNet version 1 is running faster, and this is due to the complexity of YOLO v5 model. Discussion. The performance of the 2 architectures was promising in general, but YOLO v5 performance was better than SSD MobileNet version 1 in all of the metrics due to its complexity and it's relatively newer than the SSD MobileNet, so it's expected. But this comes with the cost. The YOLO v5 needs a huge processing power, but SSD MobileNet version 1 is easily deployed in embedded systems or mobile phones. YOLO v5 was in our project. YOLO v5 was deployed on Google Cloud platform GCP for cloud inference for the video diagnosis feature due to its heavy processing power need. But unfortunately, we couldn't finish the connection between the app and the GCP.
The last part of our project is the deployment on a mobile application. To deploy any deep learning model on a mobile application, we have to follow the given steps. The first one is to train and evaluate the model. After that, we have to convert the trained model to TensorFlow Lite. Then, building the application using the Flutter framework, and at the end, deploying the model on the application and testing its performance. Unfortunately, because TensorFlow Lite was recently added to Flutter, we had the following limitations. The first one is that the YOLO v5 architecture is not supported yet by Flutter, and therefore the only model deployed on the application was the classification model, which was responsible for the plant disease identification. And thereby, the only possible way to add our custom object detection models to the application is by using a server, and therefore the need for an internet connectivity. Now, let's see our application user interface. Before we start, we will check that our device is not connected to any network. We open our application and we will see the loading screen. Here we have the home screen, which contains a list of the crops that are available for diagnosis. We have a list of vegetables and a list of fruits. The second screen is the diagnose screen, which is used to monitor our plants. The last screen is the settings screen. Now, to diagnose our plants, we open the diagnose screen and click on diagnose your plant. We either upload a picture or take a picture. Let's try a picture. Here we have a grape leaf which is healthy. The accuracy of the prediction is 100% and the model says your plant is healthy. We click on save results. Let's try another one. Here we have an apple leaf which is diseased. The accuracy of the prediction is 100% and the model gives a recommendation to stop the spread of this virus. We click also on the Save Results button. Now let's try taking a photo. Here we are taking a picture of a grape leaf. Let's see what will be the prediction. We click on OK. And then the prediction is available. We have a grape leaf which is diseased, the accuracy is 100% and we have a recommendation. We click on the Save Results button as well. Now, the other functionalities which are not available by the time being because the incompatibility between our YOLO v5 model and the Flutter framework. When we open these buttons, we can see that we have 4 crops to check their maturity, and this functionality will say to be available soon, as long as we connect our model to the server and the server to our application. The same one for the garlic seeds. The last screen, which is the settings screen. Here we can choose the language, which we have 3 languages. We have English, French and Arabic. Changing to French, the language of the application is changed. Let's try the Arabic language. We will try to diagnose our plants using the Arabic language to see. Here we have the prediction, the accuracy of the prediction, and a set of recommendations set in Arabic. We click on Save Results. Let's go back to English. The second functionality of the settings screen is to clear cache. Let's see our application cache. It is 30.80 megabytes. We go back to our application, we click on Clear Cache, and we will see that the cache is cleared. We go back to our application, we have a Share the Application button, which is used to share the application with others. Now, let's see the results that were saved in the phone. We open our gallery, and then we can see a folder which contains the different diagnosis results that were saved before.
general conclusion, training a convolutional neural network model from scratch is a tedious process, and therefore it is preferable to use transfer learning. The proposed system was capable of doing real-time prediction for the plant disease diagnosis locally while maintaining a good prediction accuracy and response time. Because of the deep learning limitations, when a plant belonging to a new class is diagnosed, our application output a random prediction even if its probability is low. In cloud, inference of the proposed model of crop maturity and seed viability showed an outstanding result and proved to show correct detection of the boxes and classes. Future work. As a future work, we are planning to generalize our system on a larger dataset, especially for maturity and seed state detection, by adding more crops and seeds, because we had a big problem in collecting this dataset and finding suitable ones for our task. And collect a dataset for plant water stress to include later on the application, as it was not available at the time we were working on the project. And finish the connection between the Google Cloud platform and our application, since it was not established due to the lack of the time. And here is the result of our Google Cloud platform inference for the tomato and apple maturity check and the garlic seed viability.